Before we learn how to write proofs, we first need to understand how to formalize statements mathematically. This brings us to propositions, which are nothing but mathematical statements which one may wish to prove. A proposition is the simplest form of a mathematical statement. It contains no variables and it's either true or false, never both. Sometimes it's easy to determine whether a proposition is true or false, and sometimes it's not clear. Even though we know that it's a proposition, we may not necessarily know whether it's true or false. Let's take a few examples. So the examples here, 4 greater than 5 and 4 less than 5, very clearly these are propositions, and very clearly the first one is always false, the second one is always true. Our next example is the following. For all integers a and b, a plus b the whole square is a square plus b square plus 2ab. The first thing we'd like to ask is this a proposition? Because it seems to depend on variables a and b, and we've said that a proposition is a statement which contains no variables. We'll see a little later why this statement is in fact a proposition. For now, let's focus on whether it's true or false. If you aren't very careful, you might be tempted to suggest that this statement is true. However, if you look carefully, the proposition states that this algebraic expression a plus b the whole square is a square plus b square plus 2ab is true for all integers, whereas we know that this expression is only true for non-negative integers. And therefore, as it stands, this statement is in fact false. The next statement is that every even integer greater than 2 can be expressed as a sum of two prime numbers. Let's take a few examples to see if this proposition sounds reasonable. Let's start with 4, right? We're talking about even integers greater than 2. Let's start with 4. So 4 can be expressed as a sum of two prime numbers, 1 plus 3. 6 can be expressed as a sum of two prime numbers, 1 plus 5. 8 is 3 plus 5, and so on. Can go all the way, for example, to 100. 43 plus 57. You could potentially try out more examples as well. So it seems that this proposition might be true. However, at this point, we cannot conclude whether it's true or false. Why? Because the examples that we've considered here do not constitute a proof. In particular, this proposition is a statement about an infinite set of values, the set of all even integers greater than 2. And we cannot determine whether it's true or false just by taking examples, in particular, just by taking a finite set of examples, which is what we're trying to do here. And therefore, as it stands, we do not know whether this proposition is true or false. Now, it turns out that this particular statement is actually the Goldbach's conjecture and is one of the most important open problems in number theory currently. Now that we've taken a look at certain examples of propositions, let's take examples of statements which are not propositions. So this statement here, n plus 17 equals 20, is this true? Well, the statement is true when n is equal to 3 and it's false otherwise. And therefore it depends, because it depends on the variable n, it depends on the value which the variable n takes. This is not a proposition. N times 0 is equal to 0. Now we do know that this statement is always true. Likewise, when we say n times 0 is 1, we do know that this statement is always false, regardless of what value n takes. Having said that, just because it's always true or always false, it does not become a proposition. In particular, the statement depends on the value of the variable n, and therefore we cannot say that it's a proposition. Quite often we do want to talk about propositions whose truth value depends on the value of one or more variables. In particular, we want to make general statements about implications for the set of all natural numbers or all integers which satisfy a certain property, and so on. And this brings us to predicates. Here's an example of a predicate. The predicate P of n states that n is a perfect square. going to assume here that n is an element of z plus, so the variable takes values in z plus, which is the set of all positive integers. So z plus here happens to be the universe of discourse. That's the notation to specify what are the possible values for the variable in question. Okay, so if we look at P of 4, we know that P of 4 is true. We know that P of 7 is false. P of 16 is true, and so on. We could consider several examples like this. And this brings us to the definition of what a predicate is. Now, a predicate has a true or false assignment for every single value of its variable. So for any given value of its variable, it has to either be true or false, but not both. So in particular, if you look at P of 4, P of 7, P of 16, these are all propositions. So for every single value assigned to its variable, it in fact is a proposition. And this brings us to the ways in which we can convert a predicate into a proposition. The first way, which we just discussed, is to assign it a value from the universe of discourse. Another way to convert a predicate into a proposition is to quantify it, and that's what we're going to talk about now. There are two ways of quantifying predicates. The first is universal quantification. The universal quantification of p of x, the predicate, is the proposition p of x is true for all x in the universe of discourse. This is denoted by for all x p of x using this notation. We can view the statement for all x p of x as a very large AND statement. For example, if we consider the predicate p of x, x is a perfect square, where the universe of discourse for x is z plus, then the proposition for all x p of x is nothing but p of 1 and p of 2 and p of 3 and so on. Now we know that this proposition is false because p of 2 is itself false. This brings us to the following observations. For all x p of x is true because it's an AND statement if p of x is true for every single x. For example, the statement every even integer is divisible by 2 is true because it's true for every even integer. Likewise, to show that for all x p of x is false, we just need to demonstrate one counterexample. It's false if there's even a single x for which p of x is false, like we did in the case of the proposition about n being a perfect square. We knew that p of 2 is false because 2 is not a perfect square. Next, we talk about existential quantifiers. The existential quantifier says that a statement must be true for at least one value in the universe of discourse. So the existential quantification of predicate p of x is the proposition p of x is true for some x in the universe of discourse. It's denoted by this symbol, there exists symbol, and we read it out as there exists x p of x. The statement there exists x p of x can be viewed as a very large OR statement. Like before, if we take the example p of x, x is a perfect square, there exists x p of x can be written as p of 1 or p of 2 or p of 3 and so on. Now this is a proposition whose value is true because we know that p of 1 is true. this brings us to the following observations. To prove a proposition of the form that exists x p of x, we just need to show that there is some x such that p of x is true. However, to show that the proposition that exists p of x is false, we need to show that it's false for every single value of x. Now that we've understood quantifiers, let's rewrite some of the statements we saw earlier in terms of quantifiers. So here's the first statement. For all a in z, the set of integers, for all b in z, a square plus b square plus 2ab is a plus b the whole square. Now, this could also be written more succinctly as for all a comma b in z. Note that C is the universe of discourse for the variable a as well as for the variable b. Now, I'd like to point out one thing. When we looked at this proposition, we said this seems to depend on variables, and yet we call it a proposition. Now, the reason for this must be clear to you by now. We've taken this predicate a plus b the whole square is equal to a square plus b square plus 2ab and converted it into a proposition by using universal quantification. But note that the universal quantification is not just over one variable, but over both variables a and b. Now, we can combine universal quantification of multiple variables. We can also combine it with existential quantification of various variables and so on. Let's take a look at the second statement, which states that every even integer greater than 2 can be expressed as a sum of two odd numbers. Observe that this is not the Goldbach's conjecture. We know that every even integer greater than 2 can be expressed as a sum of two odd numbers, and this statement is in fact true. Now, because the statement talks about very specific kinds of integers, even integers greater than 2, odd numbers, and so on, it's a little bit more complicated to state this mathematically. But let's give it a shot. We know that every even integer is of the form 2i in z plus. Since we're talking only about even integers greater than 2, I'm going to restrict my space to z plus, the set of positive integers. Every odd integer can be expressed as 2j plus 1, where j again is in z plus. Again, I can restrict my attention to odd integers that are greater than 0. Now, how do I write the statement mathematically? So let's give it a shot. For all I in z plus, there exists j comma k in z plus such that when I sum the odd numbers, so remember that j and k are going to specify my odd numbers, 2j plus 1 and 2k plus 1. So when I sum these odd numbers up, I need to get the even integer that I'm interested in, and in particular I'm talking about even integers greater than 2. So when I is in z plus, the even integer will be 2i plus 2. So in particular, if I is 1, then I'm going to get 4. If I is 2, I'm going to get 6, and so on. So I'm able to make a statement about all even integers greater than 2. Okay. So here's the final statement. For all I in z plus, there exists j and k in z plus such that 2j plus 1 plus 2k plus 1 is equal to 2i plus 2. And this is the way we mathematically write the statement every even integer greater than 2 can be expressed as a sum of two odd numbers. Okay, one thing I'd like to point out is that when it comes to combining quantifiers, the order really matters. In particular, if in this statement over here I had put the there exists condition before the for all condition, then the statement would be something like this. So if I said for all j comma k in z plus, I'm sorry, if I'd said there exists j comma k in z plus such that for all I in z plus 2j plus 1 plus 2k plus 1 is equal to 2i plus 2, then this statement is clearly rubbish. In particular, what I'm saying in this statement over here is that there exist odd numbers which generate every single even integer out there when you add them up together. And we know that this is obviously false. So the key point here is that the quantification, the order of quantification, is very important. This brings us to the end of this segment. To sum up, we learned about propositions and quantifiers and saw that the order of quantification really matters. The main take-home message is that quantifiers can be used to express ideas in an unambiguous manner. They'll become really important going forward as we learn how to write rigorous proofs.